Hello all, very good evening. Let us get started. All right, so today we are going to discuss about a few model building aspects, so like feature engineering methods, as well as we are going to discuss about the model validation techniques. Then we'll get into uh, the XGBM and LGBM techniques, right? Okay. So let me give you the flow of the data science project that we have discussed in one of the few sessions, previous sessions. Okay. So we'll have the data. So then we'll perform the EDA technique. EDA technique is basically exploratory data analysis technique to find out any issues are there in the data or any opportunity for the data transformations, missing value imputations. All those things will address those problems as part of this EDA technique. Then the next step is feature engineering. Okay, so feature engineering. What is the objective of feature engineering? So objective of feature engineering is to identify the best features out of all the features that we have in the data set. Okay, and also uh, come up with the new features by make use of the existing features. Let us say I have the features like f1, okay, f2, f3, like this. You have the different features. So the feature engineering also involves, so in creating the new features, let's say I have a feature, new feature, so that I can create based on this. So f3 minus f2 by f1, and that gives me new feature. So that also will be done, so as part of this feature engineering. And this kind of feature fabrication, or so creating the new feature, requires the domain knowledge. So how do we know that? You have to subtract these two features, then divide by feature one. So when you have the sound domain knowledge, then this will be possible. Okay, but also one is this creating the new features, the other one is identifying the best features out of all these features. So I have, let's say I have 100 features, or I have 2000 features. Are we going to use all of these features while building the model? You don't have to. Okay, so handling these 2000 features would be a difficult task, challenging task, right? So in this case, what we do is we will identify the best features which are very, very important to address our problem. So narrowing down this feature list to a best feature set is also part of feature engineering. So once this is done, then we'll go for the model building, right? Model building. So then model validation. Model validation. So then we'll go for the model deployment. Model deployment, and if at all the model accuracy is not good, then we'll go back to the data set. Okay, so here, then again, we will see whether the data that we have collected is up to mark, or is good data, or so we have to include more and more data points or more features. So that would discuss, and again this process goes on. Okay. And so if you see, so far what we have discussed about the data analysis aspects, the visualizations, and how do we analyze the data using the descriptive statistics. Okay. And also we can use the clustering technique, you can use the association rules to find out the patterns from the data. And also we have seen a few algorithms. So as part of this model building, we discussed about the linear regression, we discussed about the logistic regression, and we also have discussed about the decision tree based methods so far. That means, so we have a fair idea about what is a model and how do we, what is the concept behind these models. Now we are going to discuss about this. So why we have discussed about model building? There is a reason. Okay? So because we are going to discuss, we are going to use this decision tree based methods as part of feature engineering. Okay, so to get that idea, so I've discussed the model building this. Then we are going back to the feature engineering step. So once we discuss this, then we'll discuss about the model validation, and then again we'll go back to these different models. So that is the flow that we are going to follow. Yeah. So now we are going to understand what are the data mining techniques that are available to find out the best features out of all the features that we have. Okay. So then we'll go to the model validation techniques. So how do we validate the data? How do we validate the models? And how do we identify the accuracy for a given model? So that is what we are going to understand. Yeah. So broadly, we have three techniques which are popular in the industry for feature engineering. One is a univariate selection, recursive feature elimination (RFE), then tree-based feature selection. So this is what actually I was referring to, tree-based. So you can use any tree-based methods like C5.0 or CART or Arano forest. So these uses internally different measures, right? Like gain impurity and the information gain. So based on that, we can identify the best features out of all the features. Right? So that is where we are going to use the tree-based methods. All right. So feature engineering is a process of selecting the features in your dataset that contributes the most to the prediction variable. Okay. So identify the best features, so that contributes most to the y variable, and also fabricating new variable by making use of the existing variables. Okay, so when you say feature engineering, so there are two aspects in this. One is to fabricate a new feature or construct a new feature and identify the best feature. Okay, identify the best features. So these are the two activities so would be there as part of this feature engineering. And fabricating the new features, this requires some amount of domain knowledge. That means which feature you have to combine with other features so that you will get a meaningful feature. Then identifying the best features also requires some amount of domain knowledge, but so this can be done fairly using the data mining techniques. And what are those data mining techniques? As we discussed, univariate selection and also the recursive feature elimination and tree-based methods. Just apply these methods, we will get the best features. And why do we have to do this? One is if you have a huge feature set, a huge number of variables. So as we discussed, that is a little challenging task for us to handle. And also it requires a good amount of time for the training of the model. And also, if you have unnecessary variables in the data, irrelevant features in the data, the accuracy might go down, and also it overfits the data. Noisy data or unnecessary data, it overfits the data. When you work on the feature engineering, it reduces the overfitting of the model, it improves the accuracy, reduces the training time, right? Right. So feature engineering and feature selections are same, both are same. Univariate selection, the first method. So in this univariate selection, we would use chi-square test. So chi-square, so feature selection or chi-square hypothesis test, we'll use this method. And the chi-square is basically what it does is it tests the independence between the two parameters. So I'll take, let's say for example, a variable x1 and y. Okay, and so the chi-square test the independency between these two variables, whether these two are independent or these two are dependent on each other. So here the null hypothesis is independent. These two are independent. Then alternate hypothesis is these two are dependent on each other. Okay? So this is how actually we'll define the null hypothesis and alternate hypothesis. Then we'll proceed with the test. Actually, this is the test formula. Okay, so this is the observed data that we have, and this is the expected data by expected. So this is the observed and expected by expected. Yes, that's right. And then we'll conduct and we'll get the chi-square value. And this chi-square value we'll compare and we'll find out the p-value. And the procedure is same how we have discussed the hypothesis test. So if p is less than alpha, we will reject null hypothesis, saying that so these two are dependent on each other. And if the p is more than alpha, then we'll say these two are independent and this is not going to be useful so in predicting y. Okay? If p is less than, then we'll reject null hypothesis. And what is null hypothesis? These two are independent. That means there is no association between these two variables. So if p is more than alpha, yeah, so then we'll say that hey, so yeah, so if p is less than, then we'll reject this, and if p is more than alpha, we'll fail to reject null hypothesis. Okay, based on that, we'll take the decision whether the x variable is really important, okay, in predicting y variable or not. So this is the univariate selection we can use. That means I can take out each and every variable x1, x2, x3, okay, like this. I can take out each and every variable and I can apply individually one by one this chi-square test, and we can get to know the values of this. Okay, and rather than comparing this p-value, so we would follow something called as chi-square, the raw value itself, whatever the value that we get out of this test, chi-square value. If the chi-square value is very high, okay, so very high chi-square value, so that indicates that so that variable is very important. Let us say, for example, for out of these three, so x1 chi-square value have got 1100. Okay, so x2 so I have got 700, so x3 so I have got 50. So out of all these three, so I can rank them based on this value of the chi-square. Okay, so this 1100 is a highly the significant variable. Okay, so the x1, the next is x2, the next is x3. So like that we can order the importance based on a score of x chi-square. Okay. So when you say 1100 in the chi-square distribution, will get very low p-value. That is the logic here. Right. So this chi-square method, we don't have to do manually that by taking each and every variable and apply this chi-square test. You don't have to do that manually. So we have a automated method. So in the scikit-learn package in Python, and in this we have a method called uh, select k best features. Out of all the features, just apply this class to the data set, and in this internally we are going to use chi-square test. Chi-square test we are going to use internally in this class. And then so this class, what it does is it applies chi-square test on each and every variable, and it gives us the score. Then based on the score, so the value which is very high, then we can understand that variable is very high, the important variable. Okay, like that we can understand, and we can apply this univariate selection. For classification, yeah, this chi-square test will apply for classification. And for regression, so we would apply various other methods like f underscore regression, mutual information regression. These are the different methods, and these are also nothing but the regression based methods. And there also will apply the hypothesis test, right, t-test. So that is where the t-test would be applied in these methods. And again, based on the t value or based on the p value, we can identify whether that variable is very important or so that is not so important in the regression equation. So like that we can understand using this univariate selection. Then the next method is recursive feature elimination, RFE. So the recursive feature elimination, it works by recursively removing attributes and building a model on those attributes that remains. Let us say, for example, I have three variables. So x1, x2, and x3. So these are the three variables, and I've used these three variables to build the regression equation or any model for that matter. I have got the accuracy of so 95%. So this is the first model. The second model, I have removed this x3. I have built the models x1 and x2. So x3 I have removed. Then the accuracy is, let's say, for example, 94.3%. Okay, 5. Then the third instance, so when I removed x2, the accuracy is let us say 81%. Okay, then a fourth one, x2, x3. I have built a regression equation using this two variables. Then accuracy is around, let us say for example, 85%. So now with all three variables, so this is my the accuracy. So here uh, by excluding x3, this is the accuracy. Excluding x2, this accuracy. Excluding x1, is accuracy. So what can we conclude out of this? What we have done is we have recursively eliminated a variable and we computed the accuracies. So without x3, what is accuracy? 94.5. So which is almost very near or almost equal to 95%. That means even though you don't include, even if you do not include this x3, still you are getting the same as this accuracy. That means, so x3 is not going to be useful in our regression equation or in the model. On the other hand, if you remove x2 from the model, the accuracy has been dropped drastically from 95% to 81%. That means, so x2 is placing crucial role. And similarly, x1 also, when you remove x1, then 95% to 85%, the accuracy has been drastically changed, decreased. That means, so x1 and x2, which are very, very important, and x3 is not going to be useful at all. So that is what the recursive feature elimination or RFE is. And generally, for classification, would use the logistic regression. So in this recursive feature elimination methodology, but you can use any method. There is no hard and fast rule, but generally we would be using logistic regression. So to build these models in case of classification, in case of regression, you can go for the random forest or you can go for the any other regression based methods. Yeah. So then we have a tree based methods. As you know, as we discussed, tree based methods, we have C5.0 for classification, and you can use cart, and you can use random forest, right? So this uses its own methodology to find out the best features for the tree split, right? So those tree split, we can identify the best features, feature one, feature two, like that. So we can order the importance of these features based on the Gini impurity, based on the information gain, and that itself is actually the feature selection methodology. That means the feature selection methodologies are being so internally in the tree based methods. Now we can use these methods to identify the best features. So that means if you see our workflow data, EDA, okay, feature engineering, and models, right? Now, so in the feature engineering itself, we are going to use, let's say for example, C5.0 model to find out the best features. Now, the strange part here is before we all actually uh, going to build the model, before actually we are building the model, so we are using the model here, right, to identify the best features. That means, so before we get to the phase of model building, so in the feature engineering itself, we are using the model to identify best features and take those best features, and then probably can build the same model, C5.0 or ensemble methods or whatever it is, right? Yeah. Right. So these are the three methods where you can use to build the features, identify the best features. Okay. Now let me show you this implementation of these three methods in Python. Just give me a minute. Right. So this is a univariate selection, and we are going to use select k based method. The k is basically we have to give. So how many number of features that you want to select. So that is a k value, right? And so this will be used. chi-square test. So we are going to use internally. So internally we are going to use this, and the data set, okay, the same data set that we have been using, Pima Indians data set, and these are the columns features we have. Okay, read the data set, and yeah, so separate the x and y variables. This is the select k best method score function, that is basically chi-square test. So k equal to 4, number of variables we want to select, the best variables. So fit the model, then generate the score. So it gives us the chi-square value. These are the chi-square values. Now let us compare with the indexes. Like, so here we have the highest value is 2175. So that is from the index value from fourth one. Okay, so from the right. So 1 2 3 4, the test. Okay, this is the most useful feature in identifying whether a patient has the diabetes or not. Okay, so that is what actually you can see. These are fourth value from the right. That is the test, right? So based on this test, we can identify whether a patient has a diabetes or not. Then the next most useful feature is the second one from left. That is 1411. That is PLAS. Then the next one is 181. Excuse me. Yeah. So 181, which is age. Right? So based on these values, we can understand so which variable is most important. That is a univariate or select k best method. Then the next one is a recursive feature elimination, right? RFE. Right. So we have RFE from feature selection methods, and we are going to use logistic regression. And the data frame, build the logistic model here. Instantiate that class of logistic regression into the model object. Then this model we are using in the RFE class. So RFE, that logistic regression, and n features to select. Number of features to select is 3. I want to see the best top 3 features out of all this feature set. Right, now you can see here these are the features rankings, 1 1 1, because we have asked algorithm to find out the best 3 features, and wherever you see the ranks, so 1 1 1. Okay? For 3 features, the ranks 1 1 1 have been given. All right, now so you can compare the indexes with this. So PREG is the best one, age is the best one, and PEDI is also best one. Okay, so then these are two. PLAs is the best one next. Then the three is age is okay. Mass and PEDI is the best one. Age is the next best. Right. So based on the indexes values, we can identify which are the best feature set out of the all the data set. Right. Then uh, feature importance using the decision tree that we know already. Okay. So we can build the decision tree model here. Okay. Then model dot feature underscore importances. So this generates the score. So this is basically Guinea impurity. So the value, so which is high, okay, that feature is important feature. So this one is the best feature so far, that is 0.239. Then probably 127. So like that, yeah, sorry, 0.319. So these are highest value, right? So these are the best feature, then this is a best feature, like that. So we can compare the values with the indexes of the features, then we can conclude which feature is best. So probably here, if you use these 3 methods, so there is no guarantee that you would get the best feature every time with all these methodologies, because based on the understanding of the data by these models, these algorithms, it gives you the best features. But so there is no guarantee that you would get the best features, same best features across the methods. No, there is no guarantee. What you can do is probably you can apply all these models and you can take majority of the times. So which methods are giving you the best features? For example, if you see the second one, so these are PLAS. So in this, decision tree is identifying that these are best feature, and also this also identifying as a second best feature, right? So probably you can conclude that these are best feature. Also, you can compare all these models, the best features, and which is very common, and probably can take it out, or so which is commonly useless feature, and you can throw it out. So this is how actually you can identify the best features out of all these variables, right? Right. So then the next the topic is model validation techniques. So in our workflow, so we have seen right the feature engineering, then model building, then model validation techniques. Right. Since we so we know what is a model and what is a model concept, so it is good to introduce to you that model validation techniques. What do you mean by model validation techniques? Model validation techniques are, so as we, yeah, at high level as we have touched upon, so how do you test your model? Okay. So once you build the model, excuse me, yeah. So once you build the model, how do you test that model? How do you know that that model is performing, okay, up to the mark? This is my model, right? So this model is performing well or not. So how do you say that? Based on the accuracy. So if accuracy is more than let's say 85%, then probably you can say model is decent enough, right? And if it is lower than that, we can think of how we can increase the accuracy of the model. Then how do you get this accuracy? First of all, have to test it, test this model. On what you will test the model? On the test data set, I'm going to test the model. And how do you come up with this test data? So one way is, as we discussed, I have an entire data set. Divide this entire data set into two portions, train, excuse me. So train and test. This is one method that we discussed. This methodology is called as trained test split method. Then we'll use this train data for model building and test data for the testing of the model. But do we have only this methodology to test the model or to validate the model? No, we have a different methods that are available. Let us have a discussion on what are the different kinds of methodologies for model testing. The different methods are these: train test set, k-fold cross validation, and leave one out cross validation, LOCV. Let us discuss one by one. The first one is the train test split approach, wherein the data set is this, okay, and then I'll divide this into two partitions. One is train and the other one is test, and this is generally, so we'll go for 70% is 30%, but it doesn't matter, okay, even you can go for 60%, okay, 40%, and 50%, 50%. So do not go below 50% from the train data set. So at max you can have this 50-50 or 60-40, 70-30 or 80-20. But again, remember that when you change this partition, okay, the number of data points into the train and test, the accuracy should not change for a given model. Let us have, for example, with this 70-30, so I have built a model. Now I've put a 30% data set to the model and I've got the accuracy of, let's say, 85%. And when I follow this approach, again, I'm building the model. 60% is a train data and 40% is a test data. And if you use this and if you test the accuracy, if at all, if it is coming to 75%, so that means your model is not good, not a stable model. That means based on your the train and test data sets, your model accuracy should not depend on. That means model is not a stable model. You can understand like that. Yeah. Now coming to this method. Yeah. So divide the data into train and test, and we'll use this train and test to build the model as well as to predict the accuracies, to find out the accuracy of the models. And what are the advantages of this methodology? The advantage is if you have huge number of data set, you have millions of rows, millions of data points. Yeah. And this is the best method to follow. So when you have huge number of data points, then you can go for this. So that is one advantage for the train test split method. And what are the disadvantages of this method? The disadvantages are, so this method is not going to be useful. So if you want to productionize your algorithm, if you want to really use your algorithm in real life situations, then this methodology is not going to be useful at all. Because imagine a situation when you uh, build a model. For example, I have a data set 70% and 30%. The data set has been divided like this. This division so would happen randomly. Remember, this is randomly, right? Model will build a model using this and test the model using this. I have got the accuracy of, let us say, 80%. Then again, I have divided this data randomly, the same partition, so 70% and 30%. And the 70% I have built a model. With the 70% I have built a model, and this 30% I have applied to the model. So would you get the same 80% accuracy? So would you get same 80% accuracy or different accuracy? It's a different, exactly, right? Because the data changes, then definitely the accuracy would also be changed, right? Then that is a disadvantage of this method, the train test split method. That means you are going to build only one time. So on a data set, you are building a model, and other data set you are testing the model. And when you want to reproduce the results, then you cannot do that. Let's say, for example, you build a model and you have got the accuracy and you send it to the customer. Then customer will also rerun the model. The customer will not get the same results unless you keep the data, the same data points into the train and the same data points into the test. Same data points into the test, right? Now, so how this is possible? So we can retain the same data points, whatever the data points that you have tested, train the model, and whatever the data points that you have tested using seed. What is seed? So whatever the data point that you have used to train the model, you can keep that same data points in the training of the model, and what are the data points that you have used to testing the model, that you have used to test the model, the same data points you can keep track of these indexes of these data points. And that is what the seed does. The seed is nothing but it makes the randomization consistently across the multiple runs. So that is what the seed. So we can, to some extent we can solve this problem, but there is a serious flaw in this. So what is that is, see, you are saying that okay, I'll keep track of these indexes that went into testing of the model, and I can reproduce the results whatever I've got, and whenever you want to rerun the model, still you will get the same accuracies. So when you apply certain seed value to the data set randomization, and imagine that this model has been productionized, okay, the production, do you give any guarantee that the similar kind of data points you will get in the production, the same data points you will get the production? No, right? You would get a different data points from the production, from the real life events. and this model may not work on these real life data points because you have not tested on so various other scenarios. Only you have considered 30% of the scenarios and you tested your model, and this model may not work on all the scenarios, right? So that is a problem with this train test split method. Okay? But this methodology you can apply only so when you have a large data set, and we would hope that all the cases would have been covered in this 30% data set, and my model would work in a real time scenario. So that is the only hope. Otherwise, this train test split method is not going to be useful to find out the real accuracy of the model. Then what is the best method? K-fold cross validation. Okay, K-fold cross validation. So K is the user given input. Fold means number of partitions. So when I say 10-fold CV, that means 10 number of partitions have to be done on the data set. Then apply the cross validation. Let us see that. Right. So here is the illustration. So of the K-fold cross validation. Okay. So what we do is whatever the data that we have. First, let me give you the idea of this K-fold cross validation. So this is my entire data set. Let's assume that the 100% data. Let us have 100 data points in this. What we do is we would divide this into different portions based on the K value. Let us take K equal to 5. So 2, 3, 4, and 5. So this is K equal to 1, K equal to 2, 3, 4, and 5. So in each partition, we'll have equal number of data points, that is 20, 20, 20, and 20. These are all the data points. Now what we do is we will leave first partition, and from here whatever the data points that are there here, so the 80 data points I'll use for the model building. Then the leftover partition we will use for the model testing. When I use this 10 to 20 data points, I'll get the accuracy rate, so called as accuracy 1. The next iteration, so leave the second second partition and use other 80 points, build the model, and use these 20 data points for the model testing. Okay, similar thing here. So this is my total 100 data points here. These are first of all, use this for testing and remaining for the model training. I'll get the accuracy 1. 1. Then the change the fold for the testing. In this case, I'll use second fold for the testing. Then I'll get again the accuracy 2, accuracy 3. Every time change the fold for the testing. Okay, this is accuracy 5. Now the final accuracy is just I'll take the average of all these accuracies. Then that would be the final accuracy of the model. So what is the difference between the last methodology and this methodology? The last methodology is we are testing the model only one time, only on one set of data. But here, in this K-fold cross validation, so we are building the model multiple times, and every data point gets a chance to participate in the model testing. Because so here 20 data points, here different 20 data points, here different 20 data points, like that. So we are covering all the data points in one of the other iterations. We are using the data point to test the model. That means model is getting tested in all the scenarios, so as part of our data set. And this is the most robust methodology to test the model to identify the accuracy. And generally the K value, so in the industry we'll go for K equal to 10. Right? When you say K equal to 10 means 10 partitions. Right? So 10 partitions we will have, and we'll build 10 different models, and we're going to get the 10 accuracies, and we'll take the average of all those things. So that is the K-fold cross validation method. Right. So here we'll have the 100% data we'll include here, but also what you can do is let us say you have there are many different approaches. Okay, either you can include all the data points here, or what you can do is, so out of 110 data points, you keep 10 data points aside, and on this 100 you build this model, you get the accuracy, and in the end probably you can apply this 10 data points to find out the final accuracy. So this is the testing. We will keep aside for the testing of the model, and these 100 data points for the model building and model validation, right? Yeah, mostly whatever the accuracy that you have got, so from here should not change from here, right? So the final methodology is leave one out cross validation, LOOCV. Yes, yes. So testing can be more than 10%. So generally it would be 15 to 20% data points, data set will be there. But make sure that, so whenever you're testing your model, so at least, so 30 data points should be there in the test data. So this is the benchmark you can take, right? So at least 30 data points should be there. Yeah, excuse me. Right. So at least 30 data points should be there in the test data set, and it could be, so 15% or 20%. So if you have more number of data points in your data set, probably you can have, so 15-20% data points as a testing of the model, right? Then the final methodology is leave one out cross validation, or is also called as LOOCV. So this is, if you want to compare with our k-fold cross validation, k-fold cross validation, if k equal to 1, then that would become LOOCV. So we said that k equal to 5, then 5 folds, k equal to 10, then we'll divide entire data set into 10 folds. If k equal to 1, okay, so then that would become the LOOCV, leave one out cross validation. Now let us see, so how this works. I have a data set like this. Okay, so let us say we have 100 data points, first data point, second data point, like that. So first data point you leave it, and remaining 99 data points you build the model. Then this data point apply on this model and get the accuracy. Okay, then, so this accuracy one. Then the next model, leave the second data point and include the first data point into the data set, and build a different set of 99 data points. That means, so we have included this first data point into the again model training, and we have left this second data point for the model testing, and again we'll get the 99 data points, and these are model 1, model 2. Okay, then I'll get accuracy 2. So like that, every time leave one data point for testing, and remaining data points used for the model building, and here I'll get the 100 models. Then find out the, yeah, get the accuracy for all 100 models, the find the average of all those things. So this is LOOCV, leave one out cross validation. And if you have many more data points, then this methodology is not going to be useful for us, because if you have 1 million data points, 1 million data points, then 1 million times the model has to be built, then model has to be tested. It takes a lot of time. So when you have a small data points, small set of data set, probably you can apply this the leave one out cross validation. But out of all these things, which is the best method? K-fold cross validation, k equal to 10. 10-fold cross validation is the best methodology to go for. Yeah, only iterations would increase, may not be changing the accuracy. That's right. Right. Now coming to, so how do we measure the model accuracy? So we are saying that we can test the models. Okay, so have the data set, train and test, and build the model, and apply the data to the test data to the model, then compute the accuracy. What is the formula to compute the accuracy? How are you going to compute? Okay, so that is what we are going to discuss as part of this measuring the model accuracies. What are the different measures? We have a different measures like mean squared error, also called as MSE. Let us say I have y, okay, y hat. This is a predicted value using the model. Then I have the error. Error is nothing but y minus, okay, y hat. Right? This is my error. And what is the MSE? So MSE is basically the average squared error over the sample. That means whatever the error that I have, so just collect this error and take the mean of this error. Okay, mean of this error after squaring. This is we have to square it. So this one. Okay, square this and then compute the mean, and this is basically called as mean squared error. That means, see, I have a data set. Uh, whatever the test data that we are trying to apply to the model, get the predictions. Okay, get the predictions from this model for all this test data. So that is what y hat, and take the actual values from this test data, that is y, and compare the differences between this, that is error, then square it. Then this is basically mean squared error of this model. Then mean error. The mean error is, yeah, take this mean of, okay, of this error. Yeah, we'll discuss that. What are the measures for classifications? Yeah, and then mean percentage error. So MPE. The mean percentage error is basically, so after computing this E, then compute one more term like E by Y. So just see how much percentage of error is there with respect to the original Y. So that is simply E by Y. Then take the mean of that. Take the mean of that, that is mean percentage error. Then mean absolute error. Mean absolute error is basically, so whatever the error that you take the mod. Just remove that algebraic sign and then compute the mean for that. That is a mean absolute error. Right? Then mean absolute percentage error, MAPE. So this one, take the mod for this, then take the mean of this. So these are the different measures we can apply, right? Um, oh, so here is the formulas. Yeah. So mean squared error, okay, mean percentage error, mean absolute error, and MAPE. Okay, mean absolute percentage error. So this is the most popular method, and along with that, we have one more method called RMSE, root mean squared error. Okay, root mean squared error. This is also very popular, and you see this mean square, right? So just take square root of that. So this becomes RMSE. So this is another popular method. These two are very popular. So coming to accuracy measures for classification techniques. So we can find out the accuracy based on the number of correct predictions by total number of data points that we have. The best one is RMSE we can go for, or MAPE. These are the two best methods you can consider. Right. So here we have accuracy. Accuracy is basically, yeah, so we know, right? So how many number of correct predictions have been made by the model by the total number of predictions made. That is simple accuracy. And so not only this accuracy as a whole useful for us to identify the model, the health or how good is a model, but also we have to compute something different. We are going to discuss that. The confusion matrix, I hope you remembered when we discussed about the elastic regression, we discussed on this confusion matrix, right? Based on the true positives, false negatives, and true negatives. Just give you some idea about this. What are these? Okay, true positives and false positives are the terminology here. Here we have actual values, and this is a predicted values. What do you mean by actual values and predicted values? Remember, we had discussed in the last regression y, okay, y hat. Then this is 0, this is 0, 1, 0, 0, 1, 1, 1, right? And we built a matrix. So 1 1, okay, 0, okay, 0. And how many number of cases are there? 1 1, okay, one case. And 0 0, okay, we have 1 1 0, okay, we have 1. And 0 1, we have 1, right? So based on this, we'll fill this matrix, that is a confusion matrix. And this is called as true positives. You can compare here true positives and false positives. What do you mean by true positives? Let us say, here is a funny example just to make you understand in a better manner. There is a lady here, woman, and she's a pregnant. And using the model and using the diagnostics, okay, using the diagnostics, so they have found out that she's pregnant. The actual value is 1. She's pregnant. Using the models or diagnostics methods, okay, doctors have found out she's pregnant. So this is the true positive. That is a right prediction, like this. So my actual value is 1 here. My model also predicted as 1. That's a right prediction. That is a true positives. Now coming to this part. So here, so actually this is a man here, and actual value is this guy cannot be pregnant, but using the diagnostics, so the doctors found that, so this guy is a pregnant. So this is false positive. They are saying that it's a positive, the test is positive, pregnancy test, but that is not correct. It's a false positive. That is what here. Now here, this case, she's a pregnant actually, but using the test, they found that she's not a pregnant. Okay, so that is a false negative. So there is an error here, and there is also error here. So here, yes, we know that this guy is not a pregnant, and the system, diagnostic systems also found that this guy is not a pregnant. That's a true negative. Now, what are the cases out of these 4 cases? What are the cases which are correct? So this is a case correct, and here also correct, and other 2 boxes are not correct. Then we'll take these 2 cases. True positives and true negatives are correct, and these 2 are not correct. While finding the accuracy, so true positives plus false negatives, so true negatives, TP plus TN by total, all of them. Then that is called as accuracy, right? And also, based on those true positives and true negatives and all those things, we'll compute something called as recall and precision. So recall and precision, these two we would compute. And how do you compute? Again, so based on those terms that we have computed as part of the confusion matrix, and we'll use this recall and precision. So like this, so 2 into recall and precision by recall plus precision. So this method is called as F1 score or F measure. Okay. For a good model, so yeah, this is again, this should be high for a good model F1 score. This is another way of identifying whether the model is good or bad. Okay. Not only no, you should depend on not only the accuracy, but also you have to check F1 measure or F1 score, or at least recall or precision. These 2 things you have to check for a classification problem. Uh, okay, so if you depend on only on accuracy, you might get a misleading. The answers are misleading. The judgment about the model. Okay, so do not depend only on this accuracy, but also you have to check on recall and precision, which very important. Okay, on various scenarios. Okay, now let me show you how do we implement this in Python. Validation techniques. Right. Right. The first one is using the train test split method. So here is the train test split method from model selection, and we are going to build the logistic regression. Okay. The same data set we are going to use. Divide the data into train and test, X and Y. Test set size we are going to use 33%. Seed, right? So as I discussed, the seed uh, would make the randomness consistent across the multiple runs. And yesterday we have seen, right, a train test split method. So it gives us four data frames, data sets. So when you give X variables and Y variable, so test set size 33%, random state is 7. That is seed equal to 7 we have mentioned. And there is no significance of this 7. You can mention any number. And so if you want to make that a randomness consistency, you have to use the same number. So elastic regression, okay, and then model fit, then model score. Then let us see the accuracy of this model. 78% is accuracy, right? Okay. Then cross validation. So k-fold cross validation, import k-fold cross validation, elastic regression we are going to implement. Okay. So till here it is same. Divide the data into uh, the independent variables and dependent variable. Okay. So here, yeah. First we have to define the k-fold, how many number of splits we are going to have. Okay. And then elastic regression, initialize the elastic regression. Then cross validation, give the model the instantiation of the elastic regression as well as the data set. Then how many number of folds that you want to have. Here the folds are 10 folds. So then we can get the results. So what are these? These are the accuracies of the models that we have built in these 10 iterations. So here we've built how many models? 10 models, because 10 folds. So when you mention, so for each fold we'll use the model testing and the other the folds we are going to use for the model building. Like that, the 10 iteration has to happen, and that is what actually you can see the 10 model accuracies. Right. So then you can see the average of all these models, that is 77.6%. Okay, so that is the accuracy of the model. So seed is less than or equal to test, not necessarily. Yeah, you can give any number, 1 2 3 4 5 or 1000 or 10,000. You can give any number. If you use seed, the accuracy doesn't change. Okay, I can show you that. I can show you that here. Here I've used seed equal to 7, then 78%, right? Let me run this again. Okay, so now it is 1, right? So you can see I ran this is now 6. So it is 78.7. So when you run that, it doesn't change, right? So I've done multiple times and still the accuracy is same. That means when you use a seed, so the accuracy will not change. Right. So what is random state equal to none means? Yeah, in this k-fold cross validation, so there is no use to use this random state. Right? So that's where actually I made it as none. That means I'm not going to use. So we can completely remove this. So there is no point in retaining this here. Right. So if k value is more than 20, is accuracy increases. So not necessarily. Okay. See, if accuracy has to be depend on this partition, then the model, if accuracy depends on this partition, then model is not a good model. Your model should be independent of these partitions, right? So that is the logic here. And what methods, what actions would increase the accuracy of the model is basically feature engineering, outlier removal from the data, and ensemble methods. These are the only three actions, so that results in the model accuracy improvements, and also transformations, of course. So transformations, feature engineering, and then the outlier removal, noise removal, and the ensemble methods. So these things would increase the accuracy of the model, and any other things increases that means the model is not stable, not a good model you can think of. Okay, so then we have the final one, um, leave one out cross validation, LOCV. So just we have to load that required library, elastic regression, k-fold cross validation, and this is leave one out. Okay, and let us find out the accuracy here, results. So it is taking a good amount of time because it has to build those many number of models, how many number of data points are there in the data set. Okay, yeah, 77.6 is accuracy, and standard deviation is yeah, 41, and these are all the accuracies of the each and every model that we have in the data set, right? That we have in the models, 100 how many models? Almost we have built I think more than 100 models, and each value is the accuracy of a model, because only one data point will be there for each and every data point, right? For every model. And if the data point correctly classifies, then I'll get the accuracy as 100%. If the, if the data point is wrongly classifies, then the accuracy is 0. Okay, so like that, we have the accuracy for, so all the models that we have built as part of this, and the accuracy is 77.6%. Okay. So that's how we can validate the models, and so these validation methods we can use. Right. Questions? So expected practical accuracy of a model, if it is more than 80%, then you can say that is a good model. Yeah, and yeah, at the same time, not saying that if the model accuracy is 70%, 75% is not good model, but we have to use accordingly. If you're talking about the finance as well as the healthcare industry, so there the model accuracy should be very good, because these models are going to affect the directly the human lives as well as the money related issues, right? So in that case, we have to, yeah, so we have to be very little careful. And other cases, and given the context, you can identify the which is the best accuracy for that the model is built. So once the model is built, how we can use, yeah, so we have seen, right? I think as part of our linear regression, we have used the predict command. Anyway, we are going to see a few more things also as part of that. We'll discuss that how do we use for the prediction purpose. Okay, any more questions? Material, see the R, the Python codes and data sets already been uploaded in the Google Drive, I guess, right? So you can access them. And this PPTs, yeah, so PPTs we would upload in our LMS, and we'll give you the access to our LMS, so where you can refer here. Okay, so since these are copyrighted material, we cannot send it to you, but you can access these and you can go through them in our LMS. So that arrangement will do that. Right, so whenever a new test data point comes, can we add it to the, right, see when you have a new data point, if you know the class, okay, the y variable depend value for that, then you can add it to the existing data set, and you can use that for the refreshing the model. Okay, that is basically called as model maintenance. Okay, but if you do not know the y value for the data point, then that is for the prediction purpose. So you can send it to the model so that you can get the y value for that data point. Yes, yes. So we are planning deep learning also, completely on neural networks, okay, GANs and reinforcement learning and image processing. Yes, that will communicate to you. All right. So here I have to stop for today. So because I don't have power, so since afternoon and almost my battery is dead. Okay, and I'll stop here for today. And tomorrow we are going to discuss about the XGBM and LGBM, and then we will get into the neural network tomorrow. Okay. Yeah. So thank you all. Thanks for joining. And so here is attendance link, and we'll meet tomorrow, and we'll see those other topics. Yeah. So thank you all. Thanks for joining. Right. So you can submit your attendance from 6:20. Right. You cannot give the attendance now. Yeah. Just wait for a 6:20. After that, it accepts the attendance. Okay. So thank you all. Yeah. Bye.